Chapter 4 of our textbook is rather ambitious. It's tried to cram an awful lot of chemical information into just a few pages. So what we're going to try and do is keep it simple and give you just enough of an overview that you can look at what's written on the page in terms of chemical notation, chemical formula, and recognize it and understand it. So what I've got on the board are the top part of the main block of the periodic table. That's groups 1 through 8, ignoring the transition metals that sit somewhere here. Okay, now we can remember from a previous lecture that most of the periodic table are metals. Everything on the left-hand side, including the transition metals, the 10 blocks wide that sit right here, those are metals. And only this part right here are non-metals. And we know from experience what metals are because metals have their own physical properties that we're familiar with. They tend to be solids. They tend to be able to be polished to a lustrous shine. They're cold when you touch them because they conduct heat. They also conduct electricity. They make a pinging sound when you hit them, and they can be hammered into shape, and they can be extruded into wires. That's all the physical properties of a metal. Non-metals, these elements right here, well, they don't do any of that. None of that at all. Completely different. And then when it comes to chemical properties, what we see is that metals all react by a process called oxidation. You might be well aware that iron oxidizes, that it rusts. Well, it turns out that oxidation is the loss of electrons. Non-metals, because they're the opposite of metals, do the exact opposite. They react by gaining electrons in a process that's called reduction. Okay. So this is starting to sound complicated, but here's where the periodic table comes in and saves us. It turns out that everything in group 1 loses the same number of electrons, 1 electron, and everything in group 2 loses 2 electrons, and everything in group 3 loses 3 electrons. So the metals lose electrons predictably by group as you move across the periodic table. When we look at the non-metal side of the periodic table, something stands out. Group 8, helium, neon, argon, and krypton. These are what we call noble gases or inert gases. And we find these in nature existing as atoms, which is interesting because it means that they would rather stay as atoms than combine and make compounds with other material. That's something special. It tells us that this number 8 is a special number in chemistry, that when an atom has 8 electrons on the outside of the atom, in what we call the valence shell, valence, V-A-L-E-N-C-E. Valence means the outermost electrons. If you have 8 electrons on the outside of your atom, you become stable. So these atoms don't react. But the other non-metals, like in group 7, well, they're going to reduce by gaining 1 electron. 1 electron. If you're in group 6, you gain 2 electrons. And if you're in group 5, you gain 3. So the metals give away electrons progressively as they move left to right, and the non-metals gain electrons predictably as we move right to left. That leaves carbon in the middle. And carbon has the option of either gaining 4 or losing 4 electrons, and it just opts out. It's going to do a different kind of chemistry altogether. What we're shaping up to do right now is introduce you to a type of bonding called ionic bonding. Here's how it works. Metal atoms, like this sodium atom, will lose an electron. Now, electrons are negatively charged, and we learned earlier that in an atom, the number of protons, positive things, is always equal to the number of electrons, negative things. So when this atom gives away an electron, it's going to leave behind a positive charge because there are more protons than electrons left behind. This is no longer an atom, it's what we call an ion. An ion is a charged atom. And because this is a positively charged atom, we're going to call it a cation. Everything in group 1 loses 1 electron. So the sodium atom becomes a sodium ion. Everything in group 2 loses 2 electrons, so the magnesium atom becomes a magnesium ion. And we use superscripted numbers to tell us the amount of charge that's in that ion. The exact opposite happens for the nonmetals. Chlorine gains an electron and becomes a chloride ion, negatively charged, because the chlorine atom has the same number of protons and neutrons, and the same number of protons and electrons, and when you add an additional electron, you make it have a negative charge. Negative charged ions are called anions, and we change the name from chlorine to chloride. The metals, lithium, sodium, potassium, beryllium, magnesium, calcium, they all ended in ium anyway, but ium at the end of a word means positively charged. Ide at the end of a word means negatively charged. Oxygen, because it's in group 6, will gain 2 electrons and become oxide, which is O2-. Those rules are pretty straightforward, which means everything in group 1 makes a +1 cation. Everything in group 2 makes a 2+ cation. Everything in group 3 makes a 3+ cation. Everything in group 7 makes a 1- anion. Everything in group 6 makes a 2- anion. And everything in group 5 makes a 3- anion. We're ready to talk about chemical bonding now. There are 2 main types of bonding between atoms. One is called ionic bonding, that we'll see right now, and then the other is called covalent bonding. In ionic bonding, we take a metal from the left-hand side of the periodic table and we turn it into a cation. And we take a non-metal from the right side of the periodic table and we turn it into an anion. And then we make the cation and the anion stick together by attraction, because positive charges and negative charges attract one another. And when we have balanced the charges, you are done. So if I wanted to make sodium chloride, which you might be aware is table salt, I would find a sodium as an atom. It's a metal, so I will oxidize it. Sodium is in group 1, so I will oxidize it 1 time to a +1 cation. And then I will find some chlorine, which is a non-metal, in group 7, so I would reduce it with 1 electron until it became a 1- anion. And now that 1 plus and that 1 minus attract each other and balance each other out. And so my chemical formula is NaCl. I've just made an ionic compound. If I wanted to make magnesium oxide, I would find magnesium. It's in group 2 on the periodic table. It's a metal. So it would be oxidized twice to make a 2+ cation. I would then find oxygen, which is in group 6, non-metal, therefore would be reduced to a 2- anion, and the 2+ and the 2- balance each other out. And so the chemical formula of magnesium oxide, even though I may never have seen this before, they balance each other out. So whatever it is you've written down on page is correct. The chemical formula of magnesium oxide is MgO. Okay, let's do a couple more. Calcium fluoride. In all of our names, the metal goes first. The ium part leads, and then there's a space, and then the ide for the negative thing comes last. Metal, cation, non-metal, anion. So I'm going to find my metal, calcium. Calcium is in group 2, so it's going to lose 2 electrons and become a 2+ cation. Fluorine is in group 7, so it's going to gain 1 electron and become a fluoride, which is a 1-. But here, for the first time, that 2+ and this minus, they don't cancel each other out. There would still be a residual charge, positive charge left over if this fluoride added to that calcium. So it turns out that we're going to need twice as many F- to balance out a Ca2+. And we represent that this way, that the chemical formula for calcium fluoride is CaF2. A subscripted number multiplies only the atom that immediately precedes it. So there's 1 calcium and 2 fluorides. Let's make sodium sulfide. Sodium is in group 1. Everything in group 1 makes a +1 cation. Sulfide is here in group 6, so it makes a 2- anion. And again, this plus and those 2 minuses do not cancel each other out. If I want to make them cancel, I'm going to need twice as many sodiums. And I think if we think about it hard enough, we can guess what that means the chemical formula for sodium sulfide would be. That I have 2 sodiums and 1 sulfide. So I need a subscripted 2 here that multiplies the number of sodium ions by 2, but leaves the number of sulfurs alone. This is the basis of ionic bonding. And if you can do these, you can do them all. It turns out that there are 2 complicating factors for naming ionic compounds. One is the existence of things called polyatomic ions. Things like hydroxide, carbonate, sulfate, nitrate, and ammonium. These are already atoms that have bonded with other atoms but have a residual charge. And these occur in nature so commonly that what we do, instead of having to figure out everything from scratch, is we've just accepted the fact that we're going to see these repeatedly, and we're going to learn their formula. So a carbonate is CO3 with 2 minus. If I wanted to know what the chemical formula for sodium carbonate would be, I would take this whole thing, this whole chunk as a carbonate, and then find sodium. So sodium is in group 1. It's a 1 plus cation, and I would make its charge match that of the carbonate anion, and it does not, because this 1 plus and those 2 minuses don't match, which tells me that I need 2 sodiums. So the chemical formula for sodium carbonate becomes Na2CO3. Again, with the subscripted numbers, the subscript only multiplies the atom that directly went before it. So sodium carbonate contains 2 sodiums, 1 carbon, and 3 oxygens. Mostly, they're only that difficult. Occasionally, it gets a little bit more difficult. If we were to look at magnesium nitrate, we would find magnesium in group 2, so it makes a 2 plus ion, and then nitrate is NO3 minus. So now I need twice as many anions as I do cations. So what I have to do is double that whole thing. So the chemical formula for magnesium nitrate looks a little bit more complicated. Here's the 1 magnesium. There's the nitrate inside parentheses, all doubled. The other complicating factor in naming ionic compounds comes when we look at the transition metals. We haven't done anything on the transition metals at all up to this point. Well, the transition metals don't have the fixed oxidation states that the main block do. So something like iron is allowed to have a 2 plus cation or a 3 plus cation. And we will specifically name which type of ion we're looking for with a Roman numeral after its name. So we would say iron 2 chloride, FeCl2, or iron 3 chloride, FeCl3. Way back in the old ages, like last century, they had different names for those 2 compounds. One was called ferrous chloride and one was called ferric chloride. We are absolutely staying away from that naming system. We're not going to use it at all. We're going to stick with the main block as much as we possibly can because it's straightforward. It follows the rules. So ionic bonding exists between metals and non-metals. But there's another type of bonding. It's called covalent bonding. And it doesn't rely on oxidation and reduction. Instead, it relies on sharing of electrons. And covalent bonding exists exclusively between non-metals. So we see carbon combine with oxygen. Here is carbon, non-metal. There is oxygen, non-metal, to make carbon dioxide. When we're talking about non-metals, we don't always have the sense of a fixed oxidation state. And so if something appears in a chemical formula multiple times, we're going to use the prefixes mono, di, tri, tetra, penta, and hexa to let us know what combinations have taken place. You might be aware that there is a molecule out there called carbon monoxide. Carbon monoxide is CO, 1 carbon, 1 oxygen. Carbon dioxide is 1 carbon, 2 oxygens. If I take a sulfur and 2 chlorine molecules, now here's something. Oxygen itself, the oxygen that's in the atmosphere, and chlorine, which is also a gas naturally occurring, they already exist in nature as 2 atoms covalently stuck together. So what we're really doing here is attaching an atom to a pre-existing molecule. Ionic bonding leads to compounds. Covalent bonding leads to molecules. In the general public, compound and molecule are kind of used interchangeably. It's not correct, but it's not the end of the world if you get it wrong. So this sulfur and 2 chlorine molecules, which means a total of 4 chlorine atoms, would combine to make sulfur tetrachloride. Now it turns out that covalent bonding is the basis for organic chemistry and for biochemistry. So all the really important molecules in biology, the proteins, the amino acids, the fats, the carbohydrates, those are all generated by covalent bonding. Ionic bonding gives us the minerals in the world, and yes, some of those are important in biology, but they're not the basis of biology. So let's look at a few different types of chemical reactions. When we write a chemical reaction down, we write the reactants on the left, and then an arrow, and then the products. And we sometimes call this an equation, where the arrow serves the same function as an equal sign does in math, because chemical equations have to follow the law of conservation of mass, which means that the total mass of the reactants has to be in the same mass as the products, because the matter, the atoms, isn't allowed to go anywhere. It's allowed to be changed from one thing to another. The bonding is allowed to change, but the atoms cannot be created, nor can they be destroyed. So, first off, we'll look at a reaction called a combination. Now, there are multiple different types of name for a combination, but we'll keep it simple. Combination is where you take something A and something B and you stick them together, and we've made a new bond between A and B. A and B don't have to represent atoms, they can represent things that are already clustered together. But when magnesium reacts with sulfur and some heat, you make magnesium sulfide. That's it. Now we know this is a balanced equation if we count the atoms on the left, that the number of times that magnesium appears on the left is 1, and the number of times that sulfur appears on the left is 1, and the number of times that magnesium appears on the right is 1, and sulfur appears 1 time on the right. It's a balanced equation. The exact opposite of a combination is a decomposition, in which we take something that is stuck together and we break it apart into fragments. These could be individual atoms, or it could be something a little bit more complex than this. This is calcium carbonate. Calcium carbonate is what we call limestone. When you heat calcium carbonate, it breaks apart into calcium oxide, which we also call lime, and carbon dioxide. Let's go check if this is balanced. There is 1 calcium in my reactant. There is 1 carbon in my reactant and there are 3 oxygens in my reactant. And on the right hand side, there is 1 calcium here, there is 1 oxygen there, there is 1 carbon here, and then there's another 2 oxygens here. So I have 1 calcium, 1 carbon, and 3 oxygens on both sides of my equation. This is a balanced chemical equation. Let's look at an additional couple of reactions. This is a displacement where we take something that is already attached together and we bring in something external that makes a better bond to A than B does. And so it pushes it away. This is a displacement or a replacement. So if I took some magnesium iodide and I reacted it with fluorine, the fluorine would push the iodine off. That's a replacement. An adaptation of that on a bigger scale is a double displacement. And double displacements turn out to be incredibly important because these are the basis of all acid-base interactions. We haven't learned about acids or bases yet, but you've probably heard of the names of them. Hydrochloric acid and sodium hydroxide are going to react. Now, when we look at what AB means and what CD means, these, remember from the world of ionic bonding, something from the left-hand side of the periodic table, something from the right-hand side of the periodic table, something from the left-hand side of the periodic table, something from the right. So here, hydrogen from group 1, sodium from group 1, chlorine from group 7, oxygen from group 6. What's going to happen is I'm going to take A and switch its anion for the one that it's holding to the one that it's reacting with. And I'm going to do the same for the others. So HCl plus NaOH makes HOH. Oh, I think I can rewrite that as H2O, water, and NaCl, salt. This is the basis for all acid-base reactions, that an acid plus a base make water and salt. Every single time. Doesn't matter which acid and which base you put into combination, they all follow this reaction. And if you want to make sure that we have the correct number of atoms on each side, we can go ahead and balance this. On the left, there is 1 hydrogen here, plus 1 hydrogen there. There are 2 hydrogens. There is only 1 chlorine, there is only 1 sodium, and there is only 1 oxygen. And when I look on the right-hand side, there are 2 hydrogens, there is only 1 chlorine, there is only 1 sodium, and there is only 1 oxygen. This is a balanced acid-base neutralization equation performing a double displacement reaction. Let's take a closer look and have a harder think about chemical reactions, because just observing them isn't going to be enough. We are going to need to know about amounts, that if I mix 2 chemicals together, how much am I going to make? And if I need to plan ahead, how many chemicals do I have to buy because I know that I'm going to consume them? So we have to think about the ratios that these things combine with. When I look at this combination reaction, this is a combination that uses oxygen. Oxygen is supplied to us in the atmosphere as O2. It comes ready-made like this. This is a combustion. Combustion is a type of combination reaction that uses oxygen. I'm going to take some carbon, we're going to burn it in oxygen to make carbon dioxide. If I take one carbon, it will consume one oxygen molecule and it will make one carbon dioxide molecule as a product. But what exactly does that mean? Does that mean that if I took a gram of carbon, that I would also need 1 gram of oxygen and that it would make 1 gram of carbon dioxide? Well, no, it can't possibly be that, because we know that the law of conservation of mass means that because this is a combination, that the mass of the product has to be heavier than the mass of any one of the individual reactants. It's going to be the mass of all of those reactants combined. So what does the 1 mean? It's not mass. It's the number of the individual atoms. Okay. Well, how many of those do I know how to measure out from the bottle then? Here's where we have to go back and look at the periodic table. When we go and look at the periodic table, we find carbon and we find oxygen. And inside the box, there are 2 numbers. The number at the top is the atomic number. That's the number of protons. We don't need that number for today. What we do need is the mass number. That's the number of protons plus the number of neutrons. This is the mass number. It tells me that 1 atom of carbon has a mass of 12 atomic mass units, and that 1 atom of oxygen has an atomic mass of 16 atomic mass units. Well, my reactant is 2 oxygens stuck together, so the formula mass is just the atomic mass of everything that's in the chemical formula added together, is twice 16. So this oxygen weighs 32 atomic mass units, and that carbon weighs 12 atomic mass units. My reactants have different masses. So if I took exactly the same number of carbons and exactly the same number of oxygen molecules and reacted them together, I would need a different mass of carbon than I would for a different mass of oxygen. So what we need to do is just make this number make more sense. And we've invented a number, and the number is called the mole. And what the mole is a relative mass. That means if I took 12 grams of carbon, it would contain the same number of particles as 32 grams of oxygen. I've just taken the mass and made it relative. Now, there is a number that's associated with the mole. It's called Avogadro's number. It is completely unimportant. The textbook is going to want you to memorize it. You don't need to. If you ever need to use it, it's a constant. It will be written down. It will be given to you. Just know that in 12 grams of carbon, there are the same amount of particles as there are in 16 grams of oxygen atoms or 32 grams of oxygen molecules. So we can change that unit of atomic mass units into grams per mole. I've just made the numbers on the periodic table incredibly useful. This tells me that 1 mole of carbon would weigh 12 grams. That means 1 mole of oxygen molecules is going to weigh 32 grams. If I combine 12 grams of carbon with 32 grams of oxygen, I get to make 44 grams of carbon dioxide. And it just turned out that if I had measured what the formula mass of carbon dioxide is, 12 plus 16 plus 16, yeah, that's 44 grams. 44 grams per mole. Okay, let's ask a question using the mole as the middle point to find a finishing amount of product. So if I give you a number of grams of reactant, then what you can do is change mass into moles. The moles let you do what's called stoichiometry. That's the relationship, the numerical relationship. I'll write that word down. The numerical relationship between reactants and products is called stoichiometry. Stoichiometry is written in moles. Quantities are going to be given to you in grams, and they're going to be expected for you to give them back into grams, but we cannot use grams in the equation itself. So we're going to take a gram, convert it into a mole, find an answer, and then convert the mole back into the grams. Okay, so here is a question that requires us to find a value for a product. The question says, 3 grams of carbon burns in atmospheric oxygen to make carbon dioxide as the only product. How much carbon dioxide is made? Okay? Well, we're going to take a step-by-step process to answer this question. And the first thing that we need is a balanced equation. That carbon plus O2 makes CO2. Remember, O2 exists naturally. There's no point in us pretending that we can react carbon with individual O, oxygen atoms. They don't exist in nature. O2 does. Okay, so on the left I've got 1 carbon, 2 oxygens. On the right I've got 1 carbon, 2 oxygens. That is a balanced equation. It has a stoichiometry that I'm going to come back to at a later step of 1 to 1 to 1. So I have a balanced equation. Step 2, find the moles of reactants. Okay, I can do that. The number of moles is the mass divided by the atomic mass. So for carbon, the number of moles is 3 grams divided by 12 grams. Remember from the periodic table, the atomic mass of carbon was 12.011 grams per mole. Okay, the atomic mass is in grams per mole, and dividing grams by grams per mole gives me an answer that is in moles, and 3 divided by 12 is 0.25. I have a quarter of a mole of carbon. Okay? If I try to find the number of moles of oxygen that are in this reaction, 3 grams of carbon burns in atmospheric oxygen. That means my little tiny reaction gets to choose the entire atmosphere's worth of oxygen. So this value is infinite. The next part of the step says, identify the limiting reagent. Well, the limiting reagent is the reactant that is in the smallest mole quantity. That's the carbon. Carbon is burning in all of the oxygen that's in the atmosphere. So the oxygen is not holding the reaction back. The maximum amount of carbon dioxide that I can make is limited to how much carbon I put into the reaction, not by the amount of oxygen. So I have identified the limiting reagent. The limiting reagent is the carbon. The limiting reagent is the thing that you have the least of. It's going to be the thing that dictates how much you can make. Okay, use the stoichiometry to predict the moles of product. Okay, carbon is my limiting reagent. Carbon is dictating how much I could make. If I had 1 mole of carbon, I would make 1 mole of carbon dioxide. If I had 10 moles of carbon, I would make 10 moles of carbon dioxide. Well, my math has told me just by dividing the mass by its atomic mass that I actually have 0.25 moles of carbon, which is going to dictate how many moles of carbon dioxide I can make. Use stoichiometry to predict the moles of product. Yep. The moles of CO2 that you make is going to be 0.25. It's the same number. These two are going to be the same number. It's a 1-to-1 ratio. Okay. Step 5, convert moles back to mass. Well, the moles of carbon dioxide is equal to the mass of carbon dioxide divided by the formula mass of carbon dioxide. Moles is mass divided by atomic mass. This is the number that I need, the mass right here. I know the number of moles, and I can figure this number out just by adding up all the numbers that are on the periodic table. So the mass of carbon dioxide is equal to the moles of carbon dioxide. I'm going to move this formula mass of carbon dioxide across the equal sign, so it's going to cease being a denominator and start being a numerator. Formula mass of carbon dioxide. The moles of carbon dioxide is 0.25. And the formula mass of carbon dioxide is 12 for the carbon and 16 for each of those oxygens. It's 44. And when I take 0.25 moles and I multiply it by 44 grams per mole, the mole and the per mole cancel each other out, and it gives me an answer in grams. a quarter of 44 is 11. There's my answer. Every single time you follow the same process, you start with a balanced equation, you find the moles of the reactants, you carry forward in your calculation only the moles that are in the smallest quantity. That's the limiting reagent. You use the stoichiometry of the limiting reagent to the product to determine how many moles of product you've made, and then you turn moles back to mass. Okay? Can't use mass in equations. It just doesn't work. Those are mole quantities. And all that a mole is a mass divided by its atomic mass. So we're going to have to change all of our masses into moles and then back again. It's just 2 steps.